Welcome! We're about to pull back the curtain on the invisible journey your electricity takes, from a power plant that could be hundreds of miles away, right to the screen you're looking at this very second. It's a hidden world of absolutely incredible engineering, so let's dive in.
Seriously, have you ever thought about it? Every time you flip a switch, you're plugging into the very end of this massive, unbelievably complex journey. So to really get it, we're going to start at the beginning, with the gigantic electrical superhighways that crisscross the entire country.
All right, first stop, the power superhighway. This is the high-voltage distribution system, and it's basically the backbone of the entire grid. Its whole job is to move immense amounts of electricity over huge distances and to do it with as little wasted energy as possible.
Right away, engineers hit a huge fork in the road. Do you run these power lines up on poles, over our heads, or do you bury them underground? It's a massive trade-off. See, overhead lines are way cheaper to put up and a lot easier to fix if something goes wrong, but they're sitting ducks for bad weather. On the other hand, underground lines are out of sight and totally protected from storms, but they cost a fortune, and trying to find a problem can mean digging up a whole street.
And this isn't just a matter of convenience. It all comes down to cold, hard economics. Engineers even have a rule for this. It's called Kelvin's law. It's all about finding the perfect thickness for the wire. Go too thin and you save money on copper, but you lose a ton of power as heat. Go too thick and you're just wasting money on metal you don't even need. Kelvin's law is the math that helps find that perfect, money-saving sweet spot. Okay, so let's exit the superhighway and zoom in to your local neighborhood. You've definitely seen them, those mysterious fenced-in compounds that are always kind of humming. This is the next critical stop on our journey, the electrical substation.
So what is actually going on inside those humming gates? Well, you can think of a substation like a major traffic interchange for electricity. Its number one job is to take that super high voltage power from the long-distance lines and step it down to a much lower voltage, one that's safe enough to send out on the streets and into our homes.
And inside, it's like a whole team of specialized gear working together. You have these giant transformers doing the heavy lifting of changing the voltage. You've got massive circuit breakers that are like giant safety switches for the whole area. And then you have other things like surge arresters, which are basically bodyguards for the system, protecting it from things like a lightning strike. Now, one of the most critical safety features is one you can't even see. It's buried just under the surface. Engineers have to build this massive grid of copper wires underground called an earthing grid, and the design process is incredibly careful. They figure out the absolute worst-case scenario, design the grid, and then run all the calculations to make double sure that if something goes catastrophically wrong, the ground itself doesn't become electrified and deadly to anyone standing nearby.
So, with all this powerful equipment humming along 24/7, how do you make sure it all stays working? And maybe more importantly, how do you prevent a disaster before it happens? Well, that brings us to the whole science of keeping the system healthy.
You know, the thinking on maintenance has really changed over the years. The old school way was just breakdown maintenance. You wait for it to break, then you go fix it. Not great. A better way is planned maintenance, servicing things on a regular schedule whether they need it or not. But today, the smartest approach is condition-based maintenance, where you use sensors and data to actually predict a failure, so you can step in right before it's about to happen.
And that leads to a really cool question. I mean, how can you tell if one of those giant, sealed, multi-ton transformers is starting to have a problem deep inside without, ripping it apart? The answer is just brilliant. It's basically like giving the machine a blood test.
This technique is called dissolved gas analysis, or DGA. Here's how it works. When tiny little faults start happening inside a transformer, say a connection is getting too hot or there's a tiny electrical spark, it actually breaks down the special oil inside and creates specific types of gas. These gases are like little warning flags, so by taking just a small sample of the oil and analyzing it, engineers can tell exactly what kind of problem is brewing inside. It's amazing.
Okay, the power has traveled across the country, it's been stepped down at the substation. Now it's time for the final leg of the journey. We're talking about the final mile, getting that electricity from the street, through the walls of a building, and right to the outlet. And getting power inside a building is a huge project all on its own. Before a single wire gets pulled, estimators put together these incredibly detailed cost projections. A number like this isn't just a ballpark guess. It's a careful calculation that accounts for everything: the cost of labor, every single foot of wire, and every last switch, socket, and light fixture. And the actual installation? It follows a very precise set of steps. It all starts with planning and design.
then figuring out exactly the right size of wire to handle the job. After that, they install all the protective pipes or conduits, pull the wires through them, connect all the outlets and switches, and then, finally, the whole system gets rigorously tested to make sure it's working perfectly and is 100% safe.
And that word, safety, that is the single most important thread running through this entire journey. We're not just talking about protecting expensive equipment. We are talking about protecting the people who build, maintain, and use this incredibly powerful system every single day.
Because the risks are so high, being prepared is absolutely non-negotiable. Every single electrical worksite is required by law to have a fully stocked first aid box. And the contents are very specific, focusing on the kinds of things you'd need for electrical injuries, like serious burns and cuts.
In a real emergency, knowing exactly what to do can save a life. The absolute #1 priority is to safely kill the power. If for some reason you can't do that, the next step is to use something that doesn't conduct electricity, like a dry piece of wood or a broom handle, to separate the person from the live wire. That one action is the most critical, life-saving step, and everything else follows from there.
So from an economic law that decides the thickness of a wire hundreds of miles away, to a diagnostic blood test for a local transformer, all the way to that invisible safety net buried right under our feet, this entire system is a hidden marvel of engineering. So I'll ask you, the next time you flip a switch, what part of this incredible, invisible journey will you be thinking about?